Good day everyone, and welcome to another series of video lessons that would help students, teachers, and aspiring teachers master the teaching of the content and skills of basic calculus. Do you wonder how to navigate and illustrate the behavior of different functions in terms of continuity and differentiability, and how to determine the relationship between differentiability and continuity of a function? So if yes, so please join me and let's discover GeoGebra-based instructional materials in order to fully engage our learners and ourselves in the wonders of teaching mathematical truths. Start our investigation on polynomial functions. So let's have this polynomial. F of x is equal to x squared plus 3x plus 2. Polynomials are continuous functions over the entire real number line. So this means that for any polynomial function, there are no breaks, undefined points, jumps, or gaps in its graph. And it is well defined at every point on the real number system. Please observe, let's have a visual check. Again, we will be noticing that polynomial functions are smooth and continuous everywhere. Okay, so please check if there are any breaks or sharp corners. Alright, so we type here x squared plus 3x plus 2. So this is the graph of the polynomial x squared plus 3x plus 2. Alright, so is the graph smooth and continuous everywhere? So again, let's check for any breaks or sharp corners. Yes, the graph of this polynomial, like all polynomials, is smooth and continuous everywhere. What is the implication for the differentiability of a function when the function is continuous at any point on the graph? Again, please note that it does not necessarily follow that if a function is continuous at a point, then it is also differentiable at that point. So this is similar to the case of having rational functions. We will observe the relationship between the continuity and the differentiability of rational functions later in this series. However, in the case of polynomial functions, we can algebraically and visually prove that they are continuous and differentiable at any point on the real number line. In another series, we will walk through how to compute the derivative of a function without using the limit definition. And using differentiation rules or the differentiation formulas, the derivative of x squared plus 3x plus 2 is equal to 2x plus 3. And using the limit definition, we can say that the derivative exists for all x when both the right hand and the left hand limits of the derivative are equal, meaning the right hand derivative and the left hand derivative are equal. Let's begin the algebra fun. Let's find the right hand derivative and left hand derivative of the function x squared plus 3x plus 2 at x equal to 1, shall we? Let's begin with the right hand derivative. The formula for the right hand derivative using the limit definition of the slope of a secant line is f prime c from the right is equal to the limit of f of c plus h minus f of c over h as h approaches 0 from the right. Now let's substitute 1 for c. So we have f prime 1 from the right is equal to the limit of f of 1 plus h minus f of 1 over h as h approaches 0 from the right. To find f of 1 plus h, substitute 1 plus h as the value of x for f of x equal to x squared plus 3x plus 2. So we have f of 1 plus h is equal to 1 plus h squared plus 3 times 1 plus h plus 2. Then we expand the binomial square, 1 plus h squared. So we get 1 plus 2h plus x squared. Right? So the first three terms here. Then we multiply 3 by 1 plus h. We get 3 plus 3h, the fourth and fifth terms. Then we copy plus 2. After combining all terms, f of 1 plus h is equal to x squared positive 5h positive 6. Now, to find f of 1, substitute 1 as the value of x, for f of x is equal to x squared plus 3x plus 2. So we have 1 squared plus 3 times 1 plus 2. Then evaluating further using PEMDAS, we have 1 plus 3 plus 2, which is equal to 6. So we can say that f of 1 is equal to 6. So now let's compute for f of 1 plus h minus f of 1. Substitute f of 1 plus h with h squared positive 5h positive 6. Then substitute the value of f of 1 with 6. So we have f of 1 plus h minus f of 1 is equal to h squared positive 5h positive 6 negative 6. Then we zero out or cancel out opposite terms, positive 6 negative 6. So we now have f of 1 plus h minus f of 1 is equal to h squared plus 5h. Then we retrieve the limit definition. F prime 1 from the right is equal to the limit of f of 1 plus h minus f of 1 over h as h approaches 0 from the right. Next, we substitute h squared positive 5h for the numerator, being the value for f of 1 plus h minus f of 1. Next, we factor out h in the numerator. So we have h times h plus 5. Then we cancel out h in the numerator and denominator. So we now have the limit of h plus 5 as h approaches 0 from the right. Next, we perform the limit operation by substituting h with 0. So we now have f prime of 1 from the right is equal to 5. Or we say the right-hand derivative of the function is equal to 5. Now, our objective is to find the left-hand derivative of the polynomial f of x is equal to x squared positive 3x plus 2 at x equal to 1. Here are the steps to compute the left-hand derivative. So first, we compute f of 1 plus h. So we substitute 1 plus h into the function x squared positive 3x positive 2. So we now have f of 1 plus h is equal to 1 plus h squared plus 3 times 1 plus h plus 2. Then step number 2, expand the expression. So first, we apply the special product formula. We use the formula a plus b squared is equal to a squared positive 2ab positive b squared, where a is equal to 1 and b is equal to h. Substitute a with 1 and b with h. We have 1 plus h squared is equal to 1 squared plus 2 times 1 times h positive h squared, which is equal to 1 plus 2h plus h squared. Then we multiply a monomial by a binomial. We expand 3 times 1 plus h. So we have 3 times 1 is equal to 3. And then 3 times h is equal to 3h. Then we combine like terms and simplify. F of 1 plus h is equal to 1 plus 2h plus h squared. So this is the 1 plus h squared, right? And then we have plus 3 plus 3h. This is the 3 times 1 plus h, and then we have 2. Okay? We have f of 1 plus h is equal to 1 plus 2h plus h squared plus 3 plus 3h plus 2. We combine and perform 2h plus 3h, and that gives us 5h. and we combine and perform 1 plus 3 plus 2, which gives us positive 6. So f of 1 plus h is equal to h squared positive 5h positive 6. Next, we compute for f of 1. So substitute x is equal to 1 into the function. So f of 1 is equal to 1 squared plus 3 times 1 plus 2. That gives us 1 plus 3 plus 2, which is equal to 6. And we substitute f of 1 plus h minus f of 1 into the numerator of the derivative definition. First, let's calculate f of 1 plus h minus f of 1. So substitute f of 1 plus h with h squared positive 5h positive 6, and then substitute f of 1 with 6. Then we zero out and cancel out opposite terms, positive 6 and negative 6, so we just have h squared positive 5h. Now let's compute the left-hand derivative by performing the limit operation. So we substitute the numerator here with h squared positive 5h. First, let's factor out h in the numerator. Okay, so h squared positive 5h is equal to h times h plus 5. Then we cancel h in the numerator and denominator. So we just have now h plus 5. Next, take the limit as h approaches to 0 by substituting 0 for h. So f prime of 1 from the left is equal to the limit of h plus 5 as h approaches to 0 from the left is equal to 5. So we substitute h with 0, and 0 plus 5 is equal to 5. Left-hand derivative of the polynomial f of x is equal to x squared positive 3x plus 2 at x equal to 1 is f prime 1 from the left is equal to 5. Organize all the solution lines this way. So here's a sample computation and the computation of the right-hand derivative and left-hand derivative of a given polynomial. As a conclusion, differentiability of the function at x equal to 1, we computed the right-hand and the left-hand derivatives of the polynomial x squared positive 3x positive 2 at x equal to 1, and that would be equal to 5. General conclusion, since both the right-hand derivative and the left-hand derivative are equal, f prime of 1 from the right is equal to f prime of 1 from the left, and that is equal to 5, then we can say that the function x squared plus 3x plus 2 is differentiable at x equal to 1. So thank you so much for joining me and for watching this video, and I hope that you have learned something